So welcome everybody. Thanks for being there. So we're going to listen to the thesis defense of Etienne Peillard, and the jury is composed of Sarah Krimreger, Victoria Interante, Anatole Lécuyer, Jean-Louis Vercher, Guillaume Moreau as a supervisor, as well as Ferran Argelaguet et Jean-Marie Normand, and myself, Valérie Gislinck. So we let you 45 minutes to present your work, and then we'll ask you questions and make comments on your thesis. So it's time for you, Etienne.
Thank you. I will present the work I conducted during my thesis at Central Nantes and INRIA. This thesis was supervised by Guillaume Moreau, Ferran Argelaguet, and Jean-Marie Normand. It aims at characterizing perceptual biases in mixed reality, and more especially to study the factors that can induce distance misperception in mixed reality. First, what is mixed reality? In this presentation, I will use the word mixed reality to refer to every concept mixing real and virtual elements. On the one hand, we have virtual reality. Virtual reality aims at replacing real environments and real objects by virtual environments and virtual objects. While its goal is to substitute the real for the virtual, some real elements are still involved in virtual reality, such as the user's body. On the other hand, we have augmented reality. In augmented reality, virtual elements are added into the real world. The goal of augmented reality is to integrate those virtual elements in real environments. In both cases, these technologies aim to make the real and the virtual coincide. One of the major challenges is to align the real with the virtual world to be able to see and interact with it. To do so, numerous mixed reality devices can be used. Those different devices involve different technologies, each one having its own specificities. I will here present one classification based on the distance between the eye of the user and the display. According to distance, the shape of the device and the techniques used to render images will vary. The first category is near-eye displays. This category includes headsets or head-mounted displays, which are worn on the head by the users. These head-mounted displays can be non-see-through for virtual reality or optical or video see-through for augmented reality. The second category includes handheld displays, such as tablets or smartphones. Those devices allow to achieve augmented reality by superimposing virtual elements on real camera images. Finally, the last category includes all the more distant displays, such as projectors or on screens. In this case, virtual images appear or can be projected on screens to obtain virtual reality, but they can also be projected directly on real objects or on semi-transparent surfaces to achieve augmented reality. However, each of these devices has its own specificities and suffer from specific limitations. For example, mixed reality devices, and in particular head-mounted displays, have a limited field of view. Some virtual elements can be cropped due to the limits of the augmented display. Also, the vast majority of mixed reality devices use fixed lenses on screens. As such, the accommodation at which the eyes have to accommodate, the distance at which the eyes have to accommodate, is always the same and can be different from the real elements. Virtual elements will then appear blurred due to this difference. Another limitation of is the transparency of the virtual elements. Indeed, augmented reality devices that use transparent displays are not able to provide a proper occlusion. As such, the virtual elements will appear slightly transparent. Also, lighting and shadows calculation and rendering are also especially difficult in mixed reality. Overall, all those limitations lead to differences in perception between real and virtual elements. In this thesis, we will focus on the characterization of this difference between real and virtual, a characterization of these perceptual biases in mixed reality. But first of all, what is perception? Perception is the process that transforms reality into an inner representation of this reality. This process, the perceptual process, is very complex, and I will just here present a simplified version of it. This process can be divided in several steps. First, the stimuli. The stimuli are all the elements external to the observer's body that will create what will be perceived. Then are the psychological responses. These steps take place inside the observer's body and transform the external stimuli into a signal. Then, and it's where the magic of the human mind occurs, this electrochemical signal is transformed into an inner representation. This step contains perception, the fact that the observer sees something, and recognition, when the observer realizes what this something is. These two last steps heavily rely on the observer itself. They can be affected by knowledge, repetition, training, or states of mind. Finally, the last step of the perceptual process is action. Action is usually considered as the main goal of the perceptual process. When interacting with perceived elements, the observer can then close the perceptual loop. Represented here, the perceptual process as a very simple linear process, but it has to be noted that this process is much more complex and each step can have an influence on all the other ones. In this work, to study the effect of mixed reality on perception, we will focus on two different steps. First, the stimuli. As I presented before, what is presented to the observer can be impacted by the technological limitations of mixed reality devices. As such, virtual stimuli will be different from real stimuli, and this difference will impact perception. Second, we also want to identify the specific inner effects that can occur in mixed reality. Since the environment provided is different, so can also be the inner representation of this environment. Then, during this work, we focus on three main challenges. First, we want to highlight the intrinsic factors that can impact perception in mixed reality. Then, we also aimed at characterizing the effects of the technical limitations that will impact perception. And finally, we wanted to provide methods to compensate the previously described factors in order to improve perception. To tackle these challenges, we have to focus on one specific sort of perception. First, we focused on one specific sense, vision. Indeed, vision is the main sense of the human beings and is also the main sense which is stimulated by mixed reality devices. Then, we choose one metric to evaluate visual perception, the perception of distances. During our work, we conducted a pair factor approach to evaluate the specific effect of each factor, the technical and the intrinsic factor. Our goal was to separate the effect of each factor to evaluate its specific effect on perception. Finally, knowing the effect of some specific factors, we wanted to use and to improve one factor in order to improve perception. I will now present some elements of the scientific literature that study distance perception in mixed reality. You can see here a Sankey diagrams of studies evaluating distance perception in augmented reality. It appears that a lot of different factors can be considered. The distance evaluated, the reporting techniques used, the type of the device, but also the device's characteristics, such as accommodation, but also field of view, rendering, latency, and even object or background related elements. To analyze these studies, we will focus on the specific effect of the technical limitations on mixed reality devices impacting depth cues. These depth cues are the information gathered to evaluate distances using vision. Different classifications of these depth cues can be proposed, and I will present here one classification using 3 categories. The first category is the oculomotor cues. These are all the cues that involve the eyes of the observer. It contains vergence, which is a cue provided by the fact that the eyes have to rotate to converge at one point. Accommodation, related to the contraction of the eye's lens, which contracts to adjust the focal distance and make the image sharp. And finally, the binocular disparity, which relies on the fact that the 2 eyes have a slightly different position. The second category is pictorial cues. It includes every cue that can be obtained within a 2D image. For example, linear perspective, relative size, atmospheric blur, occlusion, etc. The last category contains cues related to movement. Since vision is a continuous phenomenon, the relative movement of objects can allow the observer to infer distances. The 2 main cues in this category are optical flow and parallax. Moreover, the weight, the importance of these depth cues will vary with distance. At close range, the most important cues will be the oculomotor cues, while at longer distances, the strongest cues are the pictorial cues. The evolution of these cues' strengths will define 3 spaces according to the distance between the observer and the object: the personal space, the action space, and the vista space. This denomination also traduces the fact that the observer can or cannot interact with an object according to the space in which it is located. Like previously for devices, we can see that distance is already a factor interacting with distance estimation. I will now present the specificities of mixed reality on several of these cues. First, the most important are binocular disparity and convergence. In fact, what we usually refer as 3D images are stereoscopic images. 2 different images presented to each of the eyes to provide a proper binocular disparity and convergence cues. These cues are recognized to be the most important and most effective depth cues for mixed reality devices. However, some other cues can be inaccurate, as we already presented before. This inaccuracy, this conflict between the stereoscopy and the other cues, can lead to a reduction of the effect of this cue on distance estimation. The main cue that can be inaccurate in mixed reality is accommodation. Since most of the mixed reality devices display the virtual elements at a fixed distance, the eye has to accommodate at this distance to see the image sharp. However, this distance can be different from the actual distance of the virtual object provided by the other cues. Yet, dissociating accommodation and vergence is known to lead to a biased perception toward the accommodation distance. In particular, many mixed reality devices use collimated displays. This means that the focal plane for virtual images is placed at infinity. This has been reported to be responsible for an overestimation of distances for the virtual objects in augmented reality. However, when providing a close enough but still inaccurate accommodation distance, this bias can be significantly reduced. Moreover, another issue of this difference between accommodation and vergence is the vergence-accommodation conflict. Under normal circumstances, the eyes usually converge and accommodate at the same distance. Then the human visual system is used to this consistency, and vergence and accommodation are linked. Yet, dissociating vergence and accommodation in mixed reality will lead to a conflict, the vergence-accommodation conflict. This conflict is known to induce visual fatigue and, more generally, to hinder visual performances. Finally, many other cues can be affected by the computational and rendering limitations of mixed reality displays, and in particular, lighting and shadows. It's very difficult to render proper lighting and proper shadows in augmented reality because the devices based on semi-transparent screens can only add light and not subtract it. However, using dedicated shading models or specific shadow techniques such as drop shadows, which are shadows placed just below the objects, can significantly improve distance perception in mixed reality. Besides this depth cues related factor that can impact distance perception in mixed reality, I want also to detail the intrinsic factors that can impact this perception. Intrinsic factors are known to impact distance perception in general. For example, gender and age are known to impact distance perception. However, I mentioned previously the effect of accommodation in mixed reality. But with the age, the strength of the accommodation cue is changing. Elder people are used to a deteriorated accommodation and as such rely less on this cue. Then age, which is an intrinsic factor, can impact distance perception in mixed reality in combination here with accommodation. More generally, elements linked to knowledge, learning, and repetition can have an impact on distance estimation. This effect is important because people can be trained in mixed reality and get used to the virtual nature of the environment. Finally, other inner factors, such as emotions, are also known to impact distance estimation in augmented reality. In this short presentation of the state of knowledge, we showed that many factors can influence distance perception in mixed reality. Then, our objective was to evaluate the effect of some intrinsic and technical factors on distance perception in mixed reality. In this work, we conducted a per-factor approach in order to evaluate the specific effect of several factors. To do so, we conducted 4 series of user experiments. First, we focused on one intrinsic factor in virtual reality using dedicated experiments to get rid of any other external factors. In this experiment, we tried to evaluate the global shape of the visual space. Then, we conducted 2 series of experiments to evaluate the effect of technical limitations on the perception of distance in augmented reality. Our goal was to compare real estimates with virtual estimates in augmented reality. The first experiment focused on the effect of rendering and position of shadows in augmented reality. This work was conducted in collaboration with Yuan Gao from the Beijing Institute of Technology. The second experiment focused on the study of exocentric distances, the estimation of distance between 2 objects. Finally, after this per-factor analysis, we wanted to use one specific factor to improve perception. We conducted an experiment using retinal projection displays, which are focal-free displays, in order to improve perception in augmented reality. This work was conducted in collaboration with Yu Taito from the Tokyo Institute of Technology. First, we will focus on one specific intrinsic bias. Our goal here is to evaluate the shape of the visual space when no other external factors are involved. First, it has to be noted that in real environments, the perception of distance is not isotropic. The perception of distance will vary according to the direction of the observer's gaze. This effect will be impacted in particular by the shape of the environment. However, when we look to virtual environments, these environments are usually oriented. Forward is a specific direction. The virtual elements are built around one specific direction, and for perceptual studies, the objects are always presented in front of the participant. Moreover, the participant is usually seated facing one direction. Then we ask the following question: what happens when we look to the side? To answer this question, we conducted 4 user experiments involving 80 participants in total, including the pilot study. The 2 first experiments were conducted to evaluate the effect, and the two following ones were control experiments. The goal of these experiments was to measure the difference in distance estimation between objects placed in front and objects placed on the side of the observer. The protocol was similar for all those experiments. First, the participants can see one object in front of them and one on the side. The objects were presented one after another in a random order. Then, participants had to choose which one was the farthest. One object was always at the same position, and the other one can be farther or closer. The color of the sky was used to communicate with the participants without any written sign that could impact distance perception. For the first experiment, the object on the side was placed at 60 degrees, right or left, and the second experiment, it was at 15, 30, or 45 degrees. We computed the results using psychometric curves to reveal the difference in distance perception between on the side and in front objects. For the first experiment, with objects placed at 60 degrees, we showed that objects placed on the side are perceived as being further than objects placed in front. The results from the second experiment show that this effect is not noticeable at 15 degrees, but it increases with the viewing angle. The effect measured at 45 degrees is similar to the one obtained at 60 degrees. Then, we wanted to be sure that the measured effect was not due to external factors and was an inner bias. In fact, we noticed that when looking on the side, the participants were not always moving completely their head. Then, object on the side was seen on the side of their field of view. We know that peripheral vision is deteriorated due to the structure of the eye, but also due to the optical limitation of the lenses. So maybe this deterioration of the peripheral vision could be responsible for the observed effect. Then we conducted an experiment similar to the first one, but using a sound signal to guide the participants' head movement. With this signal, we ensured that the object was in the center of the field of view of the observer when it appears. However, results showed a similar bias. Distance to objects on the side are still overestimated compared to in-front objects. Thanks to our two alternative first choice protocol, which is very sensitive to differences, we wanted to know if this effect is still present when more depth cues are provided. We use the same protocol as before, but using a stimuli which provides more depth cues. The results with this configuration were similar to the previous ones, showing the same anisotropy of distance perception, but with a weaker effect. With this series of experiments, we showed that visual space in virtual reality is affected by an internal bias, the anisotropy of distance perception. With different experiments, we tried to get rid of all the potential external factors that could have been responsible for this bias. As such, we believe that this bias is mostly an inner bias. A potential explanation for this bias can be related to the head movements. When looking to an object on the side, the observer has to move its head. The movement could increase the effort needed to reach the object and then be responsible for the overestimation of the distance. Moreover, the oriented nature of environments in virtual reality, with objects placed in front and observer seated facing one direction, could increase this bias. Then, this effect should be considered when designing virtual environments and perceptual studies. We have studied an intrinsic factor in virtual reality. We will now focus our work on augmented reality, trying to evaluate the differences between real and virtual in distance estimation. The first factor we tackled is a rendering factor, shadows. In particular, we studied the effect of the rendering on the position of shadows on distance estimation in augmented reality. In fact, shadows are considered as an important depth cue. In augmented reality, they help to anchor virtual elements in the real environment. However, the calculation of coherent and realistic virtual shadows is a major challenge in augmented reality. As I presented before, to compute and to render proper shadows is difficult for the augmented reality devices. As such, we wanted to know in what extent virtual shadows can impact distance perception, and also to define which are the most important characteristics of shadows in augmented reality. To do so, we conducted 2 user studies in order to evaluate the effect of the rendering and the position of virtual shadows on distance perception in augmented reality. I will not present here the 2 experiments in detail, but just focus on the main results. The first experiment studied the effect of the rendering of the shadows. We compared distance estimation for a virtual object using different shapes for the shadows: simple circle shadows, hard shadows with sharp edges, and more realistic shadows with blurred edges. These 3 shadows conditions were compared to a no shadow condition. The results show that even if the presence of shadows improved distance estimation, the shape of the shadows had no influence on this improvement. Our second experiment studied the effect of the position of the shadows. We had 3 shadows conditions, one coherent with the position of the lights, and 2 other conditions with shift light. We found that the perception of distances was mostly unaffected by the modification of the light position, except when the object and the shadows were close to the observer. As a conclusion of these studies, we showed that shadows participate indeed in distance estimation in augmented reality. They can increase the precision of distance estimation, but this effect seems limited to extreme conditions and does not seem to be affected by a precise rendering of shadows. As such, in these conditions, shadows seem to be a rather weak cue for distance estimation in augmented reality. In our third contribution, we wanted to evaluate another aspect of the effect of augmented reality on distance perception. Our goal was to characterize the effect of augmented reality on the estimation of the distance between 2 objects. Most of the studies conducted to evaluate distance perception focus on egocentric distance, that is the distance between the observer and the object. Here, we will focus on exocentric distance, that is the perception of distance between 2 objects. In fact, the most consistent result for egocentric distance estimation in augmented reality is that distance for virtual elements is underestimated compared with the results obtained for real elements. As such, we wonder if the bias that occurs from egocentric distances can also apply for exocentric distances. To tackle this question, we designed the following experiment involving 29 participants to evaluate the exocentric distance perception of observers in augmented reality. Participants were seated wearing a Microsoft HoloLens in order to display virtual objects. The real objects were placed and revealed by a mechanical bench. This bench and the calibration performed for virtual elements ensure that the virtual and the real objects can be precisely placed at the same depth. The participants were asked to evaluate the distance between the objects and reproduce this distance using the spheres placed in front of them. 4 conditions were tested for this experiment. 1 condition with 2 real spheres, 1 condition with 2 virtual spheres, and 2 mixed conditions with 1 real and 1 virtual sphere. First, our results reveal a general overestimation of distances of around 25% compared to the actual distances. This effect applies to every condition. We believe that this result is linked with the answering protocol. The distances tested during the experiment was always smaller than the shoulder spacing of the participants. It was probably more natural for participants to move the spheres a little further apart when performing the task. However, thanks to our design involving real and virtual stimuli, we were able to compare results between each condition and get rid of this global bias. We analyzed the results using a general linear mixed model and conduct pairwise comparison between the different conditions. The first major result of this experiment is that 2 virtual objects are perceived closer one to each other than two real objects. This result is in line with previous result of egocentric distances. So maybe, with simple effect of perspective, objects that are perceived closer to the observer are also perceived closer to each other. However, this effect can also rely on dedicated biases. In fact, we also reported an unexpected non-symmetrical behavior for the mixed condition. According to the side where the virtual and the real sphere is, distance estimation will be different. We analyzed these results using the inner lateralization of the observers, their dominant eye. Like we can be right-handed or left-handed, we can also have a right or left dominant eye. We reported the dominant eye of our participants and used this information to analyze our mixed results. We found that the virtual object, when the virtual object is on the same side as the dominant eye, the objects are perceived closer. We found the opposite when the real object is on the same side as the dominant eye. As such, the nature of the object, which is on the same side as the dominant eye, seems to determine the effect on distance estimation. For example, if an observer has a right dominant eye and the right object is virtual, then the distance between the objects will be underestimated, whichever is the nature of the other object. In conclusion, we found strong evidences that the underestimation of distances for virtual objects compared to real objects also applies for exocentric distances. Then, while the field of exocentric distances studies is still scarcely treated, the results from the egocentric distance field could allow to infer the effect of some factors on exocentric distances. Moreover, we found that internal biases are still a major challenge for perception. For exocentric distances, the internal lateralization of the participants seems to be an important factor. After evaluating several factors impacting distance perception in augmented reality, we wanted to improve this perception using one specific factor, accommodation. To influence this factor, we evaluated the effect of some new augmented reality devices, which are focal-free devices, the retinal projection displays. So, what are retinal projection displays? Retinal projection displays, or RPD, are made of a laser source and a moving mirror. Since the laser is really thin and passes through the optical center of the eye, it can project one sharp point on the retina. When the mirror moves, this point will scan the entire retina and project an image. Since no lens is involved, the accommodation of the eye has no effect and the image is always sharp. This device can be considered as a focal-free device with no focal plane. To evaluate the effect of this new rendering technology on distance estimation, we built a prototype using retinal projection modules. Since this technology is still new, there is no commercial head-mounted display using retinal projection displays, and this is the first prototype of a stereoscopic augmented reality headset using RPDs. We mounted two QD laser Retisa modules on a 3D printed frame. Our design allows to precisely position the modules in front of the observer's eyes. For our experiment, we compared this custom-built retinal projection display with a commercial optical see-through display, the Moberio BT30C. During the experiment, one of the two headsets was mounted on a frame and the participants were able to see the virtual target through the display. We recruited 21 participants and used a mixed model design for the experiment. We had two groups of participants, one using the optical see-through display and the other group using the retinal projection display. For the real sphere, we used the rail with the magnet below the bottom surface of the frame to position the target. The participant was asked to perform a blind reaching task by pointing the target with its finger without being able to see its hand. First, our results reveal a general underestimation of distances of around 20% compared to the actual distances. This effect applies to every condition. This effect is in line with other experiments using a similar answering task. Since the participants had to extend their arm to reach the position of the target, the effort needed to answer may have induced this underestimation bias. However, our design involved virtual and real stimuli, so we were able to focus on the differences for distance perception between real and virtual conditions and get rid of this global bias. To analyze the results, we performed linear regressions for real and for virtual estimates with each device. Then, we can evaluate the perception of virtual elements compared to the real perception. For optical see-through devices, we found an overestimation of the distance for virtual objects of 15% compared to the real estimates. For retinal projection displays, this bias was only of 3%. As such, retinal projection displays provide a better perception of distances than optical see-through devices. Moreover, the perception provided by retinal projection displays is better and can even match the perception of real objects. We also evaluated the difficulty of the task, recording the precision of the participants and asking them to evaluate this difficulty. Yet, our results did not show any difference in difficulty between optical see-through devices and retinal projection displays. As I presented before, the main difference between RPD and OST is the focal distance. Optical see-through displays have an incorrect focal plane, while retinal projection displays have no focal plane. In this study, our results suggest that no accommodation plane is better than a false one, that a missing depth Q is better than an incorrect depth Q. These results for perception can then guide future device development in order to provide rendering on devices in line with perception. As a general conclusion, our objective was to evaluate the effect of some intrinsic and technical factors on distance perception in mixed reality. In the first contribution, we have shown the effect of one intrinsic factor, the anisotropy of distance perception in virtual reality. This series of experiments show that in virtual environments, objects placed on the side are perceived further than objects placed in front of the observer. Considering this novel bias can influence the design of virtual elements and perceptual studies. Our experiment shows that when forward is identified as a specific direction, the perception of the visual space will be affected. Moreover, more experiments can be designed to further evaluate this bias. Here, we focus on the relative perception bias between in front and on the side. However, we could also compare these estimations in virtual environments with estimation in real environments to measure the absolute effect of this bias. Our second contribution tackled a specific rendering factor in augmented reality, shadows. We evaluated the effect of rendering and position of shadows on distance perception in augmented reality. Our results showed that shadows, rendering, and positioning are a weak cue for distance estimation. As such, the rendering of realistic shadows might not be a major challenge for augmented reality devices. Other renderings, such as drop shadows, could be more efficient to provide proper perception. Current technologies are not really able to render dark shadows in augmented reality. However, new techniques, such as subtractive rendering displays, could allow to render proper dark shadows, and the effect of these dark shadows on perception still need to be evaluated. Our third contribution focused on the potential transfer of perceptual bias from egocentric to exocentric distances. We found that the underestimation of distances for virtual objects in augmented reality also applies to exocentric distances. As such, the results of the factors studied for egocentric distances could also be transferred for exocentric distances. However, our experiments also reveal the effect of inner factors, here the lateralization of the observer, on exocentric distance perception. Studying those inner factors could be very important to be able to understand the effect of the lateralization on distance perception. Moreover, we only use 2 objects in our experiments, but more evaluation could also be performed with more than 2 objects. Adding more objects to the scene can provide more reference cues, but also provide additional biases to evaluate. Our 4th contribution aims at improving distance perception in augmented reality using focal-free devices, the retinal projection displays. This experiment shows that retinal projection displays provide better perception than optical see-through devices, a perception similar to the real perception. Then, more rendering techniques could be designed to compensate other drawbacks of retinal projection displays. Since these displays have no focal plane, for example, all the virtual objects are always sharp. As such, a blur based on eye tracking data can be added on some virtual elements which should be out of focus and maybe improve perception with these devices. Moreover, accommodation Q is known to be especially important to deal with occlusion. As such, more mixed conditions with real and virtual objects at the same time can be considered to evaluate potential ordering biases related to the lack of accommodation. We can now draw some general conclusions about all the studies presented in this work. First, with this per-factor approach, we showed that external factors, and in particular the depth cues, can impact real perception and also impact perception in mixed reality. Many specific effects impact perception in reality, and these effects are also important in mixed reality. However, we also showed that these effects can be mitigated by the inconsistency of other cues. In mixed reality, when some cues are sometimes incorrect, this inconsistency can impact all the other cues and bias perception. In particular, intrinsic factors seem to be especially important to understand perception in mixed reality. The orientation, as seen in the first contribution, and the lateralization of the participant, described in the third contribution, are all examples of intrinsic factors that can impact perception in mixed reality. Finally, we also showed, thanks to this per-factor analysis, that dedicated improvement on some specific factors can lead to a perception in mixed reality that is similar to the real perception. Those works highlighted general perspectives and future works. In terms of midterm perspective, it has to be noted that our experiments had specific parameters designed to maximize the effect of some factors we wanted to study. We evaluated retinal projection displays at near distances to maximize the effect of the accommodation cue, or used a blank environment in the first study to get rid of any external factors. However, every experiment can be complemented using different devices, evaluation tasks, different distances, or different objects. These experimental variations are infinite, but each variation can participate to the evaluation of the combined effect of all the factors impacting distance perception in mixed reality. As a long-term perspective, perception can also be used as a tool to measure the differences between what is real and what is virtual in mixed reality experiences. For example, for visualization, perception can be used to guide the choice of representations and to measure the efficiency of this representation. Also, for collaboration, perception can provide an insight into avatars and the representation of the body through the prism of the perceptual process. And finally, studies on interaction can benefit from the studies of perception in mixed reality. About this third perspective, and as I presented in the beginning of this presentation, action is the last step of the perceptual process. As such, conducting studies involving perception and interaction might lead to significant improvements of these two elements. For example, perception can help to develop new interaction techniques, and new interaction techniques can be designed to improve perception. Perhaps research dedicated to interaction and perception in mixed reality can help to close the loop of the perceptual process. The results from this thesis have led to some publication in journals and international conferences. And I want to thank my supervisors as well as all the people who participated in the production of this work. Thank you.
Thank you very much. Exactly in time. So now it's time for questions and comments. And I first invite Victoria Interante to open the game. Victoria comes from the University of Minnesota, sorry.
So first, I'd like to say that that I was really impressed with this work in many different aspects. So first of all, you started out with a very strong and well-developed theoretical grounding for the research that was done, and I think this is incredibly important and valuable to guide the questions that you were trying to answer. I was also really impressed with the cleverness, the carefulness and the cleverness of the experimental design. So each of the experiments, was designed in, with like I said before, with a strong theoretical grounding, and also, very careful control of effects. And then I really appreciated how you introduced these really clever constructions. So the mechanical device for moving the spheres and for reporting, I thought this, it represented a tremendous amount of investment of effort and also, ability in getting those setups to work. And then, I just want to say from my perspective in the US, the quantity of the results that you were able to produce is, very inspiring. I want my students to be able to see what you were able to accomplish, and so, maybe as a bit of an incentive. So after having said that, I do have a number of questions. So let me see if I can organize them. Let's see. I had some when I was reading the dissertation. I had some with the presentation. So let me see if I can find the ones from the presentation first. So these are going to be in a little bit of random order. I don't remember in your dissertation if you talked about in your last experiment with a retinal projection display, if you had observers who were elderly, like above 45, who have accommodation deficits, and if you would notice or expect a difference in the impact of using a properly accommodating display on people who've lost the ability to accommodate.
So thank you for these remarks. About this last experiment, in fact, we conducted the experiment in university. So most of our participants were students from the university. If I remember correctly, the elder of our participant was something like less than 30 years old, so they was all young. And that's something we focused on because we knew that the main effect we will find will be due to the accommodation. So we focused on people with relatively young and also without any minimum amounts of I would say correction, visual correction. We asked them if they have glasses, and we tested them for visual acuity to be sure that all of our participants who have have normal vision, and this will be not so impactful. So since to be honest, we were short on time for this experiment, so we really focused on having non-biased participants to compare the two groups of results.
Mm-hmm. Yeah, that makes sense. That was, I guess, my other question too, was for people who have different shaped eyeballs, like with the far-sighted and the nearsighted, if it would if there would be challenges in the design of the retinal projection display to make sure that the focus was correct for the different, for people who do need the corrective lenses. And then also, you talk about the internal factors. I mean, I'm just, so fascinated. I love that, I mean, the display, it seems like such a clever idea. And so that's why I'm asking you these questions about, how it would work for the general population who have these deficits. And if you have an internal, like for say, my whole life I've been farsighted, then, how would I react to seeing something on my retina that, that normally I would need to accommodate to bring into distance, but with this retinal display, I wouldn't have the same internal feedback from the, it's so like with accommodation, I remember reading a paper a long time ago about, is it the fact that it's in focus, or is it the effort, is it the signals that you're sending to the ciliary muscles to make them tighten that makes the difference, or is it the fact of the accommodation itself? And I don't know if you have any insights having worked with these devices.
Yeah, in fact, having worked with it, and also what our participants said, is that they never mention accommodation. I mean, it was quite natural for them to use the retinal projection display, because they didn't notice that the object was always sharp, because when they looked to one object, it was sharp, and they expected it to be sharp. So even in open questionnaire after the experiment, asking them how they feel during the experiment, what do they think about the purpose of the experiment, this kind of question, they never mention accommodation, because it was quite, I think, natural for them.
That makes sense. So my second question is, so in the experiment that you did with the shadows, you mentioned that that one of the things that you'd like to look at would be using like dark shadows instead of light shadows. So what I'm curious about is, do you, like one it didn't occur to me when I was reading your dissertation, but as I was listening to your presentation, I was wondering, to what extent do you have evidence that people were attending to the shadows? I could sort of imagine participants doing the experiment and just sort of ignoring the shadows and only trying to use like stereo cues or whatever. And if for some reason the shadows weren't being interpreted as shadows because they were light, they might be interpreted as, I don't know, some kind of odd reflection of light, which then was discounted just subconsciously, because we're not used to having to treating lighter areas as shadows.
Yeah, in fact, during the questionnaire, participants mentioned the strange rendering of shadows. So they identified it as shadows because they were, I think it's because they were moving with the object, so they can see the coordination between the movement of the shadows and the movement of the object. And so during the questionnaire afterward, they said this shadows was light, it was strange, but they get used to it because they do not, I mean, they just mention it and say, oh, I've seen these shadows was lighter, a bit strange, and we just, sometimes I think during the experiment, they just mention it and we just do not interact with them, just it's okay, don't worry. It's but they always identify it as shadows. They say shadows when they mention it, so I guess they understand it was the shadows of the object.
Interesting. Okay, that's super helpful. Do you think you would have seen a difference if the objects were closer to the shadows?
I think yes, and I mentioned that maybe drop shadows are more efficient because when the object and the light and the shadows are close, they're basically all aligned, and it's easier for them to use these shadows as anchoring references, and not like because most traditional shadows, realistic shadows, are not always really easy to anchor stuff because the shadows can be projected very far from the object. But when the object is close to the surfaces and close to the participant, the shadows are more easy to help as an anchor, I think.
Okay, thank you. So let me see if, I'm not sure how much more time I have. Let me see if I can find my other questions.
You still have time.
Okay, good.
Go ahead.
So in experiment 1, you talked about in your dissertation about how the objects were placed at 3 meters, which is sort of in action space of walking, and you talked about how there was that your theory of why the objects to the sides were judged as farther was because it would take more effort to reorient oneself and then to go and reach them. I'm curious if you, I mean, obviously you didn't do this experiment, so I'm just asking you to speculate, but what do you think would happen if you brought the spheres closer into reaching space? So I mean, the arm is of course anchored to the body with, with a radius that's centered at the shoulder. So, you'd have to figure out how to make things, but also, the arm is not at the eyes. I mean, with its center distance, but, I'm wondering if that might give you a way to sort of poke at that theory a little bit, the effort theory a little bit more, or what you would expect if they were in reaching distance as opposed to the action distance.
I'm not sure if this would have impacted the results because I think that if we do not change the answering protocol, participant has to see one object, then after another one, and then have to answer by using a joystick in front of them. So I don't know, because we still need to do the experiments, but I feel that since they have no other movements involved when they see the object, they just have to move their heads, and that's basically the only movement they were allowed to do, because they were seated, and we asked them to rest their backs on the back of the seat and not move, just move their head. So since they have no movement, there is no movement involved except from the head movement, I don't feel that this putting objects in the reaching space will impact the result. But if we change the answering protocol, because with objects closer, maybe we can use another answering protocol involving hands, then maybe this could have an impact on the perception of distance.
Interesting. So it's just the effort involved with the neck muscles, as opposed to the imagined effort of reaching that. Okay, that makes sense. So let's see. So I want to ask you a little bit more about the lateral bias that you saw related to the dominant eye. Can you explain a little bit more what you think the underlying mechanism for that would be? Why is it that, how would the dominance relationship between the eyes lead to the outcome that you observed?
Yeah, so first I have to state that this is our theory about this effect, because we conducted the analysis afterward. We do not expected this non-symmetrical results. So when we see those results for the mixed condition, we try to find one answer, and the most coherent one we found was this dominant eye related factor. But it can also be related to the device itself, because even if we measure the difference of luminosity of the screens, maybe there is a slight difference in alignments, for example, of the screens, or this kind of bias can also occur. So this result I think it's more like an explanation, a potential explanation of a lateralization bias, rather than a really important statement. However, I feel that when participants are asked to evaluate the distance between two objects, maybe they are used to align their dominant eye with one of the two objects. And aligning this one eye, so their dominant eye, with the object will, I think, create maybe this bias. So yeah, I think it's really linked to the way people are looking at two objects, because when there is just one object, it's I would say, easy because both eyes have to look to one object, and there is just one object. But when there is two, they can look in the middle of the two. They can look to one after another. They can focus on one of the two. So we are not exactly sure where they are looking at, and so maybe they're just aligning one object with one eye, and so the effect of the dominant eye will come from that.
Interesting. Interesting. And so, you know, you mentioned in your talk about how you were thinking of that it would be interesting to expand the experiment to have multiple points. And when you were talking about that, I was thinking about the two spheres were the references to each other, and then there was the edge of the display. And so as the two spheres are perceived as being closer to each other, you would expect that the spheres would also be perceived as being farther from the edges of the bench. You had the two AR markers, and then you had that were mounted on sort of a black block, and then the hole was cut out where you could see the spheres move. And so, you know, other reference points in that setup might be the edges of the blocks. And so would you expect that as the spheres were perceived as closer to each other, that they would also be perceived as farther from the edges of the blocks? Like, do you think that there was some sort of a, an overall, like maybe, thinking that things were closer, and because you thought they were closer, the distance would be smaller? Or, I mean, is that what you were thinking about when you were thinking about adding more points, or am I misunderstanding what you meant by the more points?
I think there's two questions here. I will answer both. First, we say to our participants where the sphere were. So they were aware that the sphere was at a specific distance, and virtual and real sphere were at this specific distance. And we even asked them if they really feel that the sphere are at this position, and they mostly answer yes, or distances which are very close. And when I say that maybe adding more objects to the scene can modify the perception, is because, yes, indeed, it can add more references, because that if, for example, if the objects are aligned, they can be used as reference for perspective cues. But also because I think that this exocentric distance bias will mostly, I mean, from what we knew from real environments, changing the orientation of the direction between two objects can also have an impact. So using several objects can also help to evaluate the global shape of this exocentric bias according to the distance and the orientation of the direction between two objects.
That makes sense. So let me look really quickly through my notes that I took earlier. I think that's pretty much everything I had. Thank you so much.
Thank you.
Thank you, Victoria. May I have a suggestion, Etienne? You could stop sharing your screen so that we can see you better.
Sure.
And now I invite Jean-Louis Vercher, who was the second written reviewer. Jean-Louis Vercher is from the CNRS, and I let you ask your questions.
Thank you, Valérie. And thank you, Etienne, for this very nice presentation, which was very clear and informative, as was your written document. I really appreciated reading your document, and thank you for this. As Vicky said, I also was very impressed by the amount and the quality of the experimental work you did in your thesis, and also by the effort you you need to go deep enough in something which is very difficult, which is the field of perception, which is difficult because I guess it's not your basic training. So I was very impressed by the fact that you discovered what are the major difficulties in our field, in field of neuroscience of perception, which is the fact that we have a lot of apparently incompatible theories. There is no consensus about how we perceive the world, and also the fact that the way we conduct an experiment may have an influence on the type of result we obtain. And this, well, both are probably linked. When you adhere to a theoretical background, you by a sort of cognitive bias, you select some type of experimental condition, which we are expecting that they will give you results confirming your background. And this is a real difficulty for us, and also I guess for people from the field of virtual reality. There is another difficulty which you did not directly address in your thesis, which is the inter-individual variability. The fact that you do an experiment with one subject, you do exactly the same with different subjects, and you do not get the same results. So you have to mix to record a lot of subjects in order to catch up a sort of what you expect to be an invariant. So what is invariant between the variability? And most of the time you forget that variability is an important factor in understanding behavior. So I have some comments and a few questions also on your experimental work. My first comment and eventually questions are on the theoretical background you develop in the first part of your document. As I said, I appreciated the effort you did to present an extensive panorama of studies on human perception of distance, which was probably, as I said previously, an impossible mission due to the huge amount of work performed during the last centuries, and also to the fact that we are still missing a unified theory of depth perception. So in clear, there is no consensus. So you have to make choices. And the problem when we enumerate the numerous factors influencing depth perception, as you did, intrinsic, extrinsic, and so on, accommodation, divergence, and so on, either technological or intrinsic. And most of these factors are studied separately because we are reductionists as scientists. We may forget that most of the time, and generally in the real world, all these factors are present at the same time. And generally, they are congruent. They give you a global figure which is coherent. Thus, the human brain is very good, is very smart in building knowledge about space based on all these factors together. And most of the time, they are congruent. When they are not, or not enough, the brain will anyway make a decision to find a coherent figure. And this is what happens, for instance, with you know the impossible figures by Escher, for instance. You see the picture, it looks correct, but if you think a little bit about it, you discover that it's not correct. But for your brain, it's okay. Everything is okay. And this is an explanation for some illusions when the information are not completely congruent or clear enough, and there are several possibilities. You select one possibility instead of others. When you are coming back to virtual reality is full of incoherences. A lot of things are not coherent. So your brain decides what is acceptable for him. And this is one of the major difficulties, is that due to inter-individual variability, due to cognitive factors such as your experience, memory, and so on, you present the same stimulus to two different persons, and we will probably get a different figure. So that was a general comment. Do you have do you want to comment on this? Do you have some opinion about this?
I don't have any opinion about it. I just totally agree, and that's, I think, the most challenging part of the work I did during these 3 last years.
Okay. So So the problem is that problem with virtuality, it is true even with analogical devices such as optical devices, a telescope, for instance. As soon as you put an artifact between your brain and the world, you modify this coherence and you change the depth perception. So probably the difficulty we encounter with this, or people from virtual reality encounter, is that it's probably impossible to solve, because it's the mere fact that you put an artifact between the brain and the world, you modify your perception of the world. Something which I would like you to comment is on the fact that you expose in your theoretical background elements contributing to distant perception, but you may forget something, is the way these informations are merged, are fused, are combined to make emerge coherent representation of space. For instance, in order to evaluate the depth of an object, I need to have an idea about its size. If you show me a sphere is a sphere. A car, I have an idea of the size of a car. If it's just a sphere or a cube, I have absolutely no idea. So I need much more information for an object which is very difficult to identify than for an object which is known. I mean, so I would like to have your opinion about the idea you have of the way the different factors you enumerated in your introduction are combined or are mutually influencing each other. For instance, size influences depth perception. And what are the consequences for virtual reality?
So first, yeah, I totally agree on especially on the size, the reference size, I mean, parts, because one of the major challenges when designing the experiment was to be sure that we measured what we wanted to measure, and to specify the factor we wanted to measure. For example, size. That's why we mostly use cubes and spheres and not other more complex objects, to be sure that size has barely no influence. The size was coherent, so when the object was closer, it was slightly bigger, but participants were not aware of the size of the object. I mean, they can see when there is some real counterparts, they can see them, but that's not objects like cars, like objects we can have a reference. So yes, it was really important for us when designing the experiment to really focus on one factor and get rid of all the other one. But the issue is what you said, is that when you get rid of all the other effects, you cannot measure them, and you cannot even measure the interaction between this the effect you measure and all the other ones. So I think that's why our first experiment is really specific compared to the other ones, because the first one was only in virtual reality, using as less as parameters possible, just one sphere with no background, no reference for background, but also for no avatar, etc. For the experiments we conducted afterward, we focused on the difference between real and virtual, and that's why I think the real experiment we conducted, the real condition of the experiment was really important, because with this comparison between real and virtual, we were able to elicit the specific effect of the factor, and also be sure that all the other factors that could interact with this effect are similar, because the goal was to get the real and virtual condition as close as possible. So I'm not sure we succeeded completely, but our goal was really to make the virtual and the real as close as possible, to only measure the effect of one factor and not in interaction with other ones.
I fully understand you, and of course we do the same thing most of the time. The problem with this perspective is that when by the way the brain is working, the sum of some informations is more, well, the result of the integration is more than the simple sum of information provided by each channel. So if you extract size perception from depth perception, I'm not sure that you really have access to the effect of the other cues on depth perception. You need to have everything. A simple sphere, a sphere can be an orange, it can be a balloon, it can be a planet. If I have no idea what it is, this may make it difficult to understand at which distance is the object, especially when it's very far from us. And this this makes the problem of distance perception is really different from what happens in my near space. I mean, the reachable space. I can manipulate object. I need to understand the distance of an object. If my pen, for instance, I need to know where it is in order to pick up. It's different for objects which are very far and now for reaching. But I would let probably Sarah will go on that direction because she is much more competent than I am on this aspect. So I won't go very far on this. I have some questions about your experiments. So again, you did a very nice set of experiments, very clever methodologies and tricks and so on. And you showed very interesting new data, particularly the one which is very confusing, very difficult to understand on the lateral anisotropy of perception. And it's very nice, but I'm still missing a link because, well, I'm a neuroscientist and I like to have a mechanistic perspective to understand the mechanisms, the way the things happen. I really have some difficulties to make a link between the data you obtain, which is very nice, and my problem, which is to better understand how the brain interprets cues about depth perception. So, and your manuscript is very elusive on this point of view. I expected you, after reading your introduction, you to make sort of link between the theoretical background and the experiment. So we'd like to give you an opportunity to do it now, during your defense. So for your first set of experiment, the one on anisotropy, so I understand that something very special happens straight ahead, in straight ahead direction. Straight ahead, it's not a clear concept because we may define straight ahead relative to the eyes, the direction in which I'm looking at, the direction in which my head is directed, but also my body. So some people working on the concept of straight ahead perception tried to manipulate these different segments. So you did it for the head, but did you try or did you have the intention to manipulate other segments such as the body, for instance? I mean, keeping the head stable in space like this and moving the body instead of moving the head. And do you expect this to have an effect on your phenomenon?
To be honest, the part about effort is the best theory we could find, given the fact that we get rid of all the other factors. So obviously our experiments does not show that this is the reason for the anisotropy of distance we found. We just found an anisotropy. We get sure that this anisotropy is not due to the technical factors, and then we try to find a new explanation. So yes, I think that this kind of, and we thought about this kind of experiments to go after the ones we conducted, to know why this effect is appearing. To be really clear, since participants were seated, we asked them to stay the back on their chair, and some of my supervisor also suggest to attach them, but I refuse this. But in any case, participants were, they're facing one direction, and this in front direction was really identified because they were all oriented in this direction, and the joystick they used to answer was also in front of them. So this direction was really clear for them. However, we thought about this kind of experiment to be sure that it's the movement of the head, because maybe the movement of the whole body can have an impact. And also I said that maybe it's the movement of the head, but it can be just the movement itself, or the time it takes for going from in front to on the side, or it can be the effort needed to move, which are three different elements which can have an effect. So sure, I think that more experiments are needed just to know the why. With our experiment, we just saw the what, and we still need experiments to explain why. Since we wanted to focus on virtual and real, so on augmented reality, we move on. That's why we conduct new experiments. But in any case, there is still experiments like the one you described that are needed to really understand if it's really linked to this effort-based theory.
Rather than to a factor linked to movement itself, I was thinking about something related to the referential, to the reference. So how is defined the direction of straight ahead and how you perceive space? For instance, in the 60s, I think it was done by 60s or 70s, Mountcastle showed by recording neurons in the parietal cortex that these cells are sensitive to the location of a target relative to the extracorporeal space, whatever is the orientation of the head when the monkey starts pointing toward the target. That means that you need to have a sort of reference to which objects are referred to. And this cannot be only eye movements or head movements, because when you perceive space, your body is in the real world. So you need to have an origin point to build your representation of space. Okay, so it was just a comment. Coming back to your next set of experiments, particularly to the shadow, you may remember a study did a long time ago by Steve Ellis. I think it was during his thesis, doctoral thesis, where he was working on a way to represent relative location of planes for the airport of Chicago. Chicago was becoming a very huge airport, and they had some difficulties to represent the relative position of the planes in a screen. And Steve showed that only a shadow projected onto a ground was enough to help to perceive the relative position of the planes near the airport. And it was even more simple just to put a line between the representation of the plane, which was just a vector, and the ground. And this is because, again, you have no idea about the size of the object you represent. But as soon as you make a link between the object and the ground, because you have a metric of a space through some lines represented or a texture represented on the ground, then the simple fact to have a link between the object, which is in a 3D space, and the ground, you remove an ambiguity about the location of the target. So it's not surprising that a very simple shadow, not related to the shape of the object, but its location of the ground is enough to help you to locate the object. Could it be that the type of explanation Steve proposed could also apply to your experiment?
I think yes, definitely, because what we found that the shadows were only important when they were close to the participants, and as such, when it was easier to anchor the shadows on the object, as I said before. So yeah, I really think that it's the same explanation. But something I want to add is that every cues, but shadows in particular, and the importance of shadows, seems to be really linked to the cue and to the task we ask the participant to perform. Because here it was the task was to measure distance between them and the object. So it was easier for them to measure the distance between them and an object placed on the floor, the shadows, rather than between them and the object in the air. So linking always the object with shadows will be important for this kind of task when they have to precisely measure distance, or for the airport example from you gave, it's also the same thing. We want to precisely know the location of the object. However, I think we can also widen this perspective because for augmented reality, sometimes we try to get realistic shadows to have realistic perception of the global space, not just one object and how to link this object in the scene, but to understand the scene as a whole. And so maybe having more realistic shadows will be helpful to understand the whole space, but not for specific objects.
Okay. And last question on your experiment with the balls. You know, when you move the balls to evaluate the relative distance, it's not a criticism, but it's just trying to understand the protocol. Your participant is manipulating some balls, 2 balls, which are very close to him at reachable distances, to evaluate the relative distance of balls, virtual or real, which are distant, some meters away from the guy. And you know, of course, that depth perception is not isotropic. So it's not a linear, you don't have a linear representation of distances. So could it be that the fact that you evaluate a distance of a far object with near objects could have an influence on your results?
Yes, definitely. At least it could have an influence, and it could be another explanation for the overall overestimation bias we found. When we try to think about the answering protocol, we ask ourselves, do we use just fingers? Because at first we thinking about asking participants just to point with their fingers the size they thought was the distance. We also think about asking them to draw a line with the same distance as the distance between the objects. And this protocol, we found it easier because they just have to move something. There is more interaction involved, and also it reproduces the same object. So they can also have a reference because at least they can see the objects they're supposed to evaluate. But as you mentioned, maybe this isotropy of the distance according to the depth can impact the protocol and then create this overestimation of overall of our results. So maybe, but in any case, that's why we always focus on the difference between real and virtual, because this difference between real and virtual shouldn't be impacted by the bias. This perspective bias, if we can say so, will be as effective should be as effective on real and for virtual elements, since they are at the same distance. So we could focus on the differences between real and virtual.
Of course. And the final comment, you said, I react to some of your last slides. You said in one slide at the end that when
maybe you want me to put it back?
Is a virtual object that is indistinguishable from a real object still perceived differently? So do you really believe, you guys from virtual reality, that this will happen someday, that we'll have virtual objects which will be undistinguishable from a real object?
I think the answer is yes. I think the more difficult question will be when. This is, and the answer to this second question is, I don't know, but in a very, very, very far time. So for now, maybe one time we will be able to provide virtual elements which are indistinguishable from real, but for today and for tomorrow, that's not the case. So we still have to focus on we have to still to study the fact that there is always differences between real and virtual, and we have to measure these differences to be able to bring back, at least to bring back perception, even if we can distinguish them, we can have the same perception of real and virtual, and then we still need to reduce this gap between real and virtual. And something else I would ask is, even if the objects the virtual object can be differentiated by if you cannot see the difference between real and virtual, but knowing that the virtual is the virtual, maybe this will impact perception. Just knowing that it's virtual, not real, but that you cannot see it.
Well, you just to remember that even if you have a nice new TV 8K and a fancy PS5, able to generate, to do some ray tracing in real time and so on. And you have photorealistic pictures. A photorealistic picture is still a picture. And a picture is not the reality. And remember Magritte. So I need to know that something is real and to, well, the fact is not that you are able to simulate perfectly the reality. The fact, the objective should not be to simulate the reality, but to stimulate the perception of reality. So this is why you need to collaborate with people from psychology and neuroscience, which are trying to understand how we perceive. Because probably, well, for instance, I'm working now with car manufacturers and people using car simulators. And my idea is that a car simulator is not here to simulate a car. A driving simulator is here to stimulate, not here to simulate a perfect car. A driving simulator is here to stimulate perfect driving. So what we need to produce is correct behavior for human, not to simulate the reality, because simulate reality probably is too hard and too complicated using the type of technologies we have now. Except that if we are able to use Elon Musk technology and to put a plug on your head and to do what is done in the Matrix. Okay. Anyway, thank you very much, Eva, for your manuscript, your presentation, and your nice answers to my difficult questions. Okay, thank you.
Thank you, Jean-Louis. Now it's time for Sarah Krim-Reger to ask her question. So she comes from the University of Utah. Go ahead. Thank you.
Thanks. So I'll just echo everyone else's comments that I really enjoyed your written document, and the presentation was very clear. I really appreciate the focus on perception. I felt like I could ask you to come guest lecture in my visual perception class and you would do an excellent job. I think that I also really appreciate the approach of comparing virtual to real. I think that's, I think that's something that's really of value in the sense that, as you've seen, we get these biases in the real world, right? So it's important to compare the virtual perception of the virtual objects to how we perceive the real world, not necessarily to what might be considered veridical in a sense. And so I think that I really appreciate that approach. Of course, in the first experiment, you couldn't do that, or at least with the paradigm that you used. So that would be really interesting to, I think, do a real world comparison to look at the anisotropy in the real world. And so overall, I was very impressed. Also, as Vicky said, we typically don't see that extent of amount of work done in a dissertation in our dissertations in the US. So it's really impressive. So I had a number of questions. So I actually, a lot of my questions and comments overlap quite a bit with Jean-Louis' comments. So I think, so I'm just trying to think what hasn't been covered, or maybe what we can talk about more. I have some specific questions about some of the experiments, and then I have a few like higher level theoretical questions. One of the things that I did have a question with I guess twice you bring up the effort hypothesis or the effort account for your results. In the first study with the targets to the side, I can see that explanation, but I think it may be a little bit weak. Like, I'm not sure that just the head rotations really would like kind of lead to that, perception of increased effort, but it would be good to test. One of the other things I was thinking in this discussion was that you could control for head movements by just using like a joystick or a controller that could move the visual world instead of moving your head. And that could give you the same visual information in terms of moving the target to the front or the side without rotating your head. So that could be potentially a way to test that hypothesis. But I had a little bit more concern with the effort hypothesis or the account in the last experiment with the reaching, because there, I think you used that explanation when people were showing underestimation of distance. Is that correct, or am I misunderstanding that?
Which are the?
So the one with the different displays.
Yeah.
Comparing the displays.
Yeah.
So they're showing
Underestimation of overall, underestimation, yes.
Right. So I think that's the reverse logic, that you wouldn't expect that if they had to reach, unless I'm misunderstanding, reaching would be greater effort, but they actually showed underestimation.
Yeah, I will just make it more clear. In the last experiment, people asked to point with their hand the location of the object, and usually the object was kind of at something a bit less than 1 meter. So it was something, I think the maximum was something like 60 centimeters or so on. So it was kind of far, so they have to extend their arm, and so to make a bigger movement. And since they have to repeat this several times, and also they were not able to see their hand, so they cannot adjust and correct their answer during the experiment. So maybe with the fact that they have to extend their arm, they were more likely to just extend it a bit less, and then this provides underestimation. And I don't know if it's more clear. So it's not related to the effort-based theory of perception, but just on the fact that people are not so likely to make efforts to reach the target, and also they cannot adjust this position. So maybe they're just getting closer and the distance can become shorter and shorter, and they cannot notice it and compensate it. So it's not related to the effort-based theory of perception, but rather than just tired of extending their hand.
I see. No, that makes more sense, that if they were not to reach as far, then they may be potentially getting feedback from that reach that told them that would inform that distance judgment to be closer. Is that's
that? Yeah, since they have no feedback, they cannot, I mean, adjust anything. So maybe they can just they've just underestimated it for this reason. You can also find the same results of, I think, usually every experiment involving movement, you can identify the resting position, and people tend to underestimate or overestimate distances in order just to stay around this resting position. So since our distance was mostly after this resting position, people wanted to underestimate the distance just to get closer to this resting position.
Okay, I see, thanks. So, let's see. Another question, I think we've talked about this a little bit already, but in the exocentric distance experiment, it was striking to me first that there was such overestimation just broadly of the frontal extents. And you've already commented a little bit about like the measure, but I was wondering if you think that was due to the measure that you used, or if you can make a broader claim that there is overestimation of frontal extents, and how that might relate to previous real-world studies that have been conducted.
Indeed, the exocentric distances in general are sometimes overestimated, but it depends on the orientation of the participant and the object. It can also depend on the position, because when the objects are in the same plane on the horizontal, at an horizontal position, they tend to be overestimated compared to objects which are one below the other. So in reality, we have this kind of overestimation sometimes for exocentric distances, not always, but not for this. I mean, the effect we found was especially important. So that's why we believe that it might be linked with perception on real and virtual objects, but maybe our answering protocol was also responsible because of the size of this effect.
Mm-hmm. Just a clarification question. Did you have, so participants could see they could look at the spheres that they were adjusting, right?
They were seeing the sphere. First, they were seeing the sphere in front of them, I mean the stimuli, and then the virtual sphere disappeared and the real sphere were hidden, and then they have to answer. So, when they have to answer, they cannot see the stimuli. They see the stimuli, and after they answer, but during the answering, they can adjust the position of the object in front of them by looking at them.
Yeah, okay. One thing that would be interesting to do would be to have them just do that adjustment just based on proprioceptive feedback. So they, without viewing those spheres, we had done some work a while ago where we asked people just to look at a target in front of them and then adjust the width between their hands, and that was not, it was a sphere or some sort of target, so we were trying to get at size perception, but very similar to an exocentric distance, and people in that case were quite accurate at just doing this based on feeling. So I wonder if there might have been some sort of conflict that was occurring because they could actually look at that interval while they were setting it, and they're comparing that to their memory of the interval that they had just seen.
And maybe also the fact that the objects were, I mean, because when you estimate the size, you can see both ends in your vision, in your field of vision. But when they were asked to adjust the position of the sphere, they were not able to see both spheres and at the same time. So they cannot compare what they see what they have seen in front of them and after what they see in front of them, because they have to positionate the object. But we're not able to really see both at the same time because they were too close from the object. So maybe this also can have biased the results just by the fact that they cannot see the actual distance of what they were answering. And we also remarked that some participants never look to their hand. They're just adjusting the distance without really looking to the object in front of them, just by feeling about the position and proprioceptive response.
Mm-hmm. Okay, thanks. So what I liked that you did an analysis on kind of the individual level for the experiment with the shadows. Not only looking at just averages, but really looking at the individual performance. And what's notable there is that there is a lot of between subject variability, something we've found in our recent AR studies as well. And I was wondering if you could comment on that in terms of why you think there may be so many individual differences. And does it, is this specific potentially to the HoloLens or the display that you're using, or do you think that there's something more, kind of general in terms of individual differences?
Yeah. So first, for this experiment, we couldn't compare the virtual case with the real case. We just compared shadows condition with no shadows condition sometimes, but it was always in virtual. So we had no comparison for the specific effect of augmented reality. And I think this is one reason, because for the other experiments, we can just average the differences of the results, and results are then more, easier to evaluate. But in any case, we look to the individual response also because we have the very weak effect, and we wanted to be sure that there is no group effect or for some participant with some specific behavior. So that's why we dig really into the evaluation of individual results. And about the variation, it's, I think, the effect of the HoloLens, not only, but mostly, or at least the fact that in our condition, the virtual objects really looked virtual. There were, since there is I won't say a lot of light, but the environment was not too dark, so the objects were not difficult to see. We can see them clearly, but anyway, they were transparent. They were clearly transparent. They were clearly virtual. Since the participant was stood up, they can move, and we ask them not to move, but they can move at least their head, and then the objects can get away from their field of view, etc., etc. So I think in our experiments, the fact that the objects were virtual was very impactful on perception, because sometimes people lose the target and then has to look for it, and say just it was in front of them, but it was sometimes difficult to see it. So I think that these individual differences mostly rely on the fact that the virtual nature of the targets was really apparent, and so will impact even more the perception.
Mm-hmm. Yeah, it's striking how we see so much variability, really using the HoloLens specifically, because you know, we can be just a group of us in the lab and looking at the avatar, like a virtual AR avatar in the real world. Some of us see it as floating, some of us see it as on the ground. So people see it at different distances, and I'm very curious to, you know, kind of think about why those individual differences occur. Like one thing that we found is that if you even just tell people to attend to the feet of the avatar, the virtual avatar, then you can kind of force it to look like it's standing on the ground, even, you know, if especially if there's no shadow there, kind of telling you if it's attached to the ground or not. So things like that, I think, you know, you could think it's interesting that there may be this kind of cognitive level of influence on perception, that it's not just the stimulus or the, you know, kind of the information that's coming through that display.
Yeah, and the fact that since the virtual elements are always sometimes floating, they cannot be anchored. Like you explain for avatar, but in general, virtual objects which appear like floating are really difficult to evaluate, to perceive. And as such, I think that this is increasing the intrinsic effect that can occur, and the fact that everyone is perceiving things differently. And these differences are even more important when there is no other cues just to calibrate.
Mm-hmm. Yeah. Okay, let's see. Okay, one more just kind of question related to the studies. So generally, you know, in the earlier studies, you're predicting and finding underestimation of distance and AR targets compared to AR or VR targets compared to the real world. And then in your last study, you predict and find overestimation in at least in the OST display in AR. Can you comment on why we might see, you know, or predict underestimation for some distances and overestimation for others?
Yeah, sure. So what I found is for close objects, usually because of the collimation of the virtual headsets, for close objects, the accommodation Q is modifying the perception, and as such, for close object, the object will be overestimated because the accommodation Q at infinity for collimated display will drive the perception. So this is for overestimation. This overestimation is, I think, only reported for close objects. And for farther objects, I think this is more difficult to explain because the underestimation we find in augmented reality, we usually link it with the underestimation we found for virtual reality. And this global underestimation, I mean, there is a lot of paper about why this underestimation occurs, but I think there is not just one explanation. The explanation I prefer, if I could say that, is that the virtual elements, in an environment where there is virtual elements, the brain will naturally, usually, reduce the perception of distance to protect him from dangerous movements, etc. So when something is unusual, it might be underestimated. And this is, I think, the most interesting proposition I can find. But for sure, the global underestimation of the distance perception in virtual and in augmented reality is still not really explained, I think.
Yeah, I think we pursued that question for many years and never really had a complete explanation. So I think that's true. It's interesting to think about that, you know, the underestimation in augmented reality is kind of similar to a similar magnitude, but it actually could be driven by different factors, right? Like, you know, one of the things that we gain from AR is that we have the real world cues, right? We have those, you know, great like linear perspective cues and rich environments that we're presenting AR in. And so that you might say then it isn't a good explanation. That those types of explanations have been used in VR, and that doesn't necessarily hold in AR. There may be other issues such as the kind of appearance that the objects are floating that contribute more to that underestimation.
Yeah, and maybe the explanation I gave is that the virtual elements, the virtual elements in augmented reality are underestimated because they're virtual. So maybe something interesting will be to evaluate the evolution of this underestimation according to the virtuality of the environments. That's an experiment I wanted to do, but I never had the time to do it. But the fact that maybe we can find the continuous evolution of this underestimation from a completely real environment until a completely virtual environment, and trying to find the modification where this effect of underestimation start to occur.
Mm-hmm. Yeah, that would be a nice study. If it might be difficult to do, but it would be very interesting. Okay, so theoretical question. So I recently got some reviews back on a paper on AR distance perception, where the reviewer said, they said this: if underestimation and other biases simply disappear via calibration, then they're unimportant. So basically, they're saying that given that we interact with our environment constantly, why should we kind of put any interest or value on these biases that we see when people are just standing still or just rotating their heads, not interacting with the environment? If it could be that these biases could be corrected with interaction, do you think that it's still important to study them, or why is it? This reviewer seemed to say that it wasn't. I'm not sure I agreed with that, but I'm interested in your comments.
I have to say that I totally disagree.
Okay.
For one simple reason, for at least one simple reason, is training on virtual training. If you consider training someone as some very difficult task and very precise task and very expensive tasks, so you design the virtual environments to train him. So at first, he will be affected by this effect of bias in perception. But with training, continuing training in virtual reality, it will just reduce this bias and finally be able to perform the task very accurately, compensating all the biases of virtual reality and learning how to do the task he's supposed to do. And once he go back to real environments and have to do the real task, there is no such biases. And then what he been to be trained is no more applicable. He just will fail the task because he learned something in virtual with the biases. So it's not always useful to compensate these biases, but I think there is use cases, and which are use cases very important today for actual use of virtual reality that rely on this reduction of the biases.
Yeah, that's great. That's what I also agree with. I mean, I think that of course interaction and calibration is important, and I really like that that's a direction that you were talking about in future work. And I think there's a lot of interesting questions. I think that we know some already about recalibration and from feedback in virtual environments, and we don't know that much. I think there's just starting to be a few studies done with interacting in AR, at least in this context of distance perception. So I think that's really important, but it's also the case that that's not going to solve all our problems. That of course we need to kind of know where the biases are coming from in the first place. And if you were, as you say, to really get this type of training in the AR system, then that's not necessarily going to be helpful for the real world if you calibrate differently. So should I end, Valerie? Yeah, okay. Okay, great. This was really interesting. I'd love to talk with you more about some of these ideas in the future.
Thank you.
Thank you very much. So now Anatole Lécuyer from the INRIA, Rennes.
Thank you, Mrs. President, and Thank you, Etienne, for this really great presentation. It was a pleasure to be here today. It was a pleasure to be part of your advisory board. So I was not officially one of your advisors. I was some kind of external consultant or external collaborator or associate member. We don't know exactly the term, but I really liked it. And I think that we had a lot of good time with the three other advisors. We had a lot of fun. We were very complementary, I believe. And we had a lot of good time. So I have only one question, because since I am an examiner, I have one question. And I'll ask it at the end, right? So first I'll make some comments and then I'll ask my question. My comments, it's more like I'm going to try to give my perception of Etienne. Of course, it's a biased perception. It's in mixed reality. It's remotely, but it's probably also subject to inter-variability, inter-individual variability with the other advisors, and maybe they will complement this perception of Etienne. My first impression, the first quality is highly producive, because in only 3 years, which corresponds to the duration of PhD in France, it's limited to 3 years, you could produce 4 contributions, actually 5 contributions, because you were unfortunately a little bit impaired by the COVID crisis and you could not conduct this final experiment, but it's quite an impressive amount of work, and it's acknowledged by a lot of great publications, including a Best Paper Award at IEEE VR. So it's quite impressive, this productivity. Second one is proactivity and creativity. I was quite impressed by our first meeting of PhD thesis 3 years ago. You came to the meeting, we asked you to think about some ideas to start, and usually the first ideas are not always in good shape, but this day you could propose like 5, 6, or 7 ideas, and it was good ideas. All of them were probably publishable. It was quite impressive, this maturity that you had already since the very beginning of your PhD. Overall, it gives the impression also of precocity. And it's also revealed by the fact that you are already, or nearly, on tenure track, and you already have your assistant professor, associate professor position actually in France, even before having your PhD, which is quite unique. I think it's, at least for us, it's the first time, but it's also quite impressive in terms of precocity. Then another perception I have is a bit moody, lunatic in French, and a bit grumpy. And you have ups and downs, and it's a bit hard to follow sometimes for your advisors, but especially for yourself. You work with peaks or waves. It's a trendy word at the moment. And sometimes it's a bit of a challenge for the boat with your advisor on it. But overall, also you have a very good sense of humor. I think it's also coming from Nantes. There is a special sense of humor in Nantes. We are discovering this in Rennes. And you are sharing this sense of humor with your 2 associates in this room at the moment. It's a very funny thing that we are sharing. We are going probably to miss these moments where we can share this good sense of humor. Overall, I think you're a great person, and you are a super teammate, super collaborator. You were very present in the team, although remote. And only present, for instance, in Rennes, in hybrid team, only once per week, only 1 day per week. And we were waiting for these Thursdays to hear your grumbling and your moaning in the corridor. It was really nice to hear that in the corridor. But also you brought your bienveillance in French, your goodwill or kindness, and it's a value that you brought to the team, actually, when we are discussing about the team values. So I owe you this one. The bienveillance. I'm still waiting for the decoration effort, but this is a private joke between you, Rebecca, and the rest of the crew also. We are waiting for your efforts for decorating the corridor before you leave. But in any way, this is coming from, now it's time for my question as an examiner. So I'd like to know what you will remember. What advice will you remember from your advisors? You can have multiple answers, but please unmute your microphone. I'd be happy to hear that.
I will start to find just one. I think the most important advice my advisor gave me, most important recommendation was do it. Just the fact that whatever is the idea, whatever is the question, whatever is the issue I underline, my advisors, you and all the other ones were always there to say that that's what, I mean, that was not especially a good idea or a bad idea or a valuable idea, but something I think about. Not really sure because I usually have a lot of different ideas, but just to pick one and go for it. And it was very inspiring, I think, to have this feedback and this advice always to just pick one and go for it until the end, until the experiment gets results and we have something. I think that's the key element of the advice all my supervisor gave me.
Okay, thank you very much, Etienne. It was really a pleasure. You're a great researcher. All the best for the next years. That's all for me.
Thank you, Anatole. And now I give myself right to talk. Jean-Louis, I count on you if I'm too talkative. Stop me. Okay, so I hope after this bias of overestimation in qualities, that I won't give you the impression of underestimation of your qualities. No, it's a joke. I'd like first to thank you and your supervisor for inviting me to be part of this defense. And I won't repeat the same compliments as the other members, compliments that I share, especially about the clarity of your writing and your presentation and the richness of your thesis. I begin with some comments and remarks and then ask you some questions. So concerning the first part, I want to insist that I appreciated very much the effort that you put in defining all the concepts that you use. It's, for me, one of the first steps of being a researcher, that is being aware that concepts do not exist by themselves on their own, that they can be seen or conceived depending on the perspective that you take on them, which implies that you have to choose the view that you adopt and you have to tell it. So it's a very important point to my view. So you did it well, except for one thing on which we'll come back later. Okay? That will be part of your question. Considering the whole structure of your thesis, I must say that I was disturbed not to find a specific part dedicated to your research questions. It's a pity because it contributes to the feeling that you jump from a question to another, from an experiment to another, picking one of the parameters that are worth studying, and that the research is kind of driven by something like opportunity, or maybe it's creativity or intuition, and that it may lack a bit of a solid vertebral column. And I think that you had all the ingredients to put this thing together and to show us a good path. I think that you missed that point. But as a researcher in experimental psychology, I also have some slight remarks. First, it's a detail, but which helps reading. You could have named your factors using a more useful code than C1, C2, C3. Instead, you could have used, for example, D5 for distances with 5 modalities, L2 for laterality with 2 modalities, left and right and so on. It's a detail, but it helps reading. Okay. More important, there is something missing in the first series of experiment. It's information about participants. Yes, I see that you have to accommodate my, I don't know why the camera, okay, sorry. I don't know why. Okay, you don't describe the participants, which is something mandatory if anyone wants to replicate your findings, and also because you are aware that it can be of importance as you've mentioned in the first part of your dissertation, but also in your presentation, for example, considering the effect of gender or whatever. And also, as Sarah recalled it, you considered it in one of your analyses. And so I wonder what you didn't specifically presented participants in the first studies. Well, maybe
you want me to answer just now? Yeah. So I think I did it for most of these studies, but I won't check now. But in any case, these results are, I mean, this information, this data have been gathered, and we can definitely add it if they are missing.
Okay, thank you. So now my questions. Oh, another detail. You use user experiment. For me, it's confusing. Is it related to user experiment, user experience? What is your user experiment for you? I'm not used to that kind of wording.
I use the word user experiment. I think that's a terminology mostly belonging to the field of virtual rated experiments, because people doing the experiment are usually users. So here, the experiments are not really about the usability or the fact that it's a device or something. The experiments are more focused on perception. So maybe the word user experiment is not the more accurate, but usually we refer to user experiment, talking about experiments involving participants on some specific devices.
Okay, thank you. So on the experimental side, I have a specific question concerning your first experiment in chapter 4. If I'm not mistaken, you presented one stimulus for 2.5 seconds, and then there is an interval, an interstimulus interval of half a second, and then there is a second stimulus for also 2.5 seconds. And only then response time is registered. You could have registered response time right from the apparition of the stimulus, of the second stimulus. Whereas in your case, your participant could have anticipated their response during the present time of the second stimulus. Why did you choose this procedure? And can you tell me how fast they were at answering?
So just to be sure, you're talking about the experiment, about the first experiment the first experiment with the anisotropy of distance. Yeah. So usually, yeah, I think usually people anticipate the results. They were really quick to answer. But in any case, we used the color of the sky to communicate, and they knew that they have to wait for them to see both stimuli before answering. So in any case, we could, I mean, the measure of the time itself is not, I think, really important here, because if in any case, the second stimuli is always presented during 2.5 seconds, and also then, and only then, they can answer. But for sure, they were really quick. I think that was something like less than a few seconds, maybe 1 or 2. Because also we say them that there is no hurry, they can take the time they want to answer, but we also tell them that they won't have more information, so there is no point of waiting to be sure. So they were rather quick to answer.
Okay, thank you. So now the main question. The only definition that I missed, and about which I'd like to listen to you, is the definition of affordance. And related to that, you have chosen a sphere as a stimulus in most of your experiments, and also a cube. Depending on the relative size, it can be a graspable object. So how do you think the graspability, the affordance, if you can define, depending on the definition you give to it, would have influenced your results on one side or the other of the continuum? I'd like to hear you about that point.
So first, about the definition. So the affordance of an object is given the shape of this object, the movement we anticipate to do to manipulate, to interact with this object. That's the definition I would give. The potential movement or interaction implied by the shape of the object. And about the effect of this affordance on our experiments, like I described before, for the first experiment, I said that since the participants, there were no links, at least maybe, I mean, just be more precise here. Most of our experiments, participants were not able to manipulate the object. They were not able, I think they were not able to imagine the object as things they have to interact with. So I don't think that the affordance of the object will be important, especially for the first and the first experiment, for example, for the anisotropy of distance, because people were not asked to interact in any case with the object. So I think the affordance in this case is not very, very important, but it might be for the experiment with the exocentric distance, where people has actually to move the object. Here, I think it could have an impact, and maybe different objects and different shapes of the object, just because of this affordance, can impact the result we will have.
I'm not sure I would agree with you, because even with just names of graspable object, it elicits some motor programming and so on. So I'm not sure, but anyway, okay. Concerning the last experiment that you weren't able to conduct, unfortunately, I'd like you to explain me why you've chosen this specific task, interactive task, because I guess, I infer, but you didn't tell, that you tried to disentangle some of the effect of vision versus proprioceptive and so on. So especially I was interested in the on-side pointing task. Could you explain more the choice of the task?
Yeah, so there is two reasons for that. First, it's the question underlined by this experiment. Our goal in this experiment, linking perception and interaction, is to define if there is some interaction in augmented reality which are more efficient than others for perception, for improving perception, or even if it impacts perception, maybe there is differences between the interaction task. So we use interaction tasks, I would say common interaction task in augmented reality. So usually to interact with objects in augmented reality, there is different interaction possible, but the pointing task is something really common. The fact that you can interact directly with an object is also quite common. And the third one we choose using the direction of the sight is also the base interaction for the first HoloLens. So that's also a very common interaction task. So we choose these three ones. So they have this importance to be common. And the other thing is we wanted different interaction with more or less movement involved. And the on-site interaction task, the direct interaction task involve, I would say, the most amounts of hand movement. So we expect this movement to be more important for the recalibration, comparing the interaction with just pointing or even side pointing. So that's why also we chose these three specific interaction tasks, was to be sure that we anticipate that the movement of the whole body and the hand in particular will impact differently this interaction and the perception of it.
I thought that you wanted to dissociate the role of, let's say, of visual information and proprioception, because if you subtract the results you obtain with the only visual pointing and from the rear pointing in front, and you consider the on-site pointing, you might have an idea if it's additive between visual information and proprioception. I thought it was directed by that, but not.
Yeah, also because since the interaction is the center of our experiment, before and after this interaction, we have a perception task. So we use a different answering protocol for this perception task, and that's why we use here no stylus or nothing, no object. It's just the hand to be able to have some completely different task for the perception task. So we have one perception task. We start with one perception task in real, then one perception task in virtual to have a reference. Then the interaction that maybe will be able to calibrate or to change something. And then we have a new perception task to see if there is a difference.
But, I would say that the perception task that you have at the beginning is visual memory task more than the virtual perception task. No, because they have to keep in mind.
Yeah, the perception task was designed not to be very closed. It was designed to be very different from the interaction, and that's why we use this specific protocol with first you see the target and after you have to point it to dissociate the stimuli and the answer, and to have something and also to have a reaching task and not a matching task, because when you keep the object, people can adjust their answering to be sure that they point in the center of the stimuli. So when it disappears, you just can keep what they remember from the distance. So I think it's more for perception studies, reaching tasks are more efficient. If you can compare with baseline, I think that the reaching tasks are more efficient.
Okay, thank you. Okay, thank you very much. And I must say, to conclude, that I like very much the fact that you propose to reverse the perspective and see the perception as a tool instead as an object of study. Thank you very much.
Thank you.
So now I take back the role of the president. And I'd like to invite your supervisor, your real ones, to take part in the discussion, and maybe Ferran, Angele, and Greg.
Okay, so I will start. So thank you, Ms. President. First of all, I would like to thank all the jury for being here. So again, as Anatole said, we have preferred to be all together in Nantes, but that's a strange time. So, and also we also would have I would have personally liked to be with Etienne in Nantes, but we could not go there due to the situation, but because we're 100 kilometers apart. But I would have enjoyed a lot being there today. So I'm really sorry for that. Yeah, and also before talking about Etienne, I would also like to thank to Guillaume, Jean-Marie, and Anatole for letting me be part of this PhD. This has been my first experience with Guillaume and Jean-Marie collaborating, and it has been an absolute pleasure. So I will look forward for future collaborations, of course. Okay, then what about what can I say to it regarding Etienne that Anatole hasn't said yet? So maybe I will try to add even more things. So and it's in line with what Anatole already said. So this autonomy. So I think you really show that you are autonomous, and yeah, of course there are ups and downs, but you are there, and you say, as you said, so when you want to do it and you have the idea and you go and you can do that, there is no issue for you at all. And also I'm really surprised and really impressed by all your qualities, because let's say that you did all the experiments from A to Z, so you are aware the main driver for the design, you implemented everything, you did all this mechanical stuff, so you like also to do stuff, and this experiment about the exocentric distance and all the stuff that you did for just that experiment, this is kind of amazing. And also the second part, so maybe the more tedious part, or the analysis or the statistics, so you really improved a lot in that respect, and you really wanted to do that yourself, and that you did it. So I'd really like to congratulate you for that. And I also would like to thank you for basically to allowing me to let's say rediscover this perception and that perception. Of course, perception has been kind of a key aspect in my research, but I think in this thesis I also gained even more knowledge, and that's thanks to you that you made that possible. Yeah, then maybe I can pinpoint maybe one record that maybe you didn't beat it, but due to the COVID, I think you almost beat it, this carbon footprint in the team. So you started really strong the first and the second year, traveling all around the world, but sorry, this last year it broke and you couldn't make the record. I'm really sorry for that. And yeah, maybe also you also maybe had the record of the failed experiments due to confinement. This last experiment, basically talking by Slack the day before, or the same day the president announced the confinement, say, oh, my experiment is ready. 10 minutes after, the president saying, okay, lockdown. So when he wants, okay, experiment is canceled. And this happened twice. So it's not a record that you would like to hold, but yeah, that happened. Yeah, maybe for the future, yeah, I would say that I would like to basically to wish you the best for your adventure in the Far West. So it's the Far West in France, because you are really going to the Far West in France. You're going to Brest, and I'm really happy that you could continue your research, and yeah, hoping that we also will be able to continue collaborating. So we're not that far away. So it's the Far West, but still we are in Rennes, so we are kind of also in the Far West ourselves. And yeah, and also maybe the last thing is this frustration for this last experiment, because would say that this last experiment is this experiment and you really try to find a solution or try to look for a way to improve perception. So I shared some discussions that we have with you, just saying that, yeah, you know, all the experiments we are discussing, we are discovering these biases or these misperceptions, but it's frustrating that you cannot improve this, or that basically you focus in the what, but you don't focus on maybe how you can improve it. But I think these last parts of your thesis are going on this line, and I would say that that's what you are willing to do in the future. So I will really looking forward to basically what happened in that direction. And yeah. And I don't have any particular question. I think that you already answered a lot of questions. So yeah, I will leave to Jean-Marie and Guillaume for the final comments. No.
Oh, thank you. It's time for Guillaume Moreau.
Thanks a lot. Well, when we started talking about your defense, I decided I would say only one thing. So it was on both a scientific and human point of view, we will truly miss you. Point is that since as a mere coincidence, we're both moving to Brest as soon as next week, this point is mostly irrelevant now, but it's the general thinking. This PhD has been a real pleasure, and of course I wish to continue working with you and the other guys in the team, obviously. So I'd like to thank also your other advisors, Anatole, Ferran, and of course, Jean-Marie. This has been a tremendous experience, and I'm looking forward to continuing doing those kinds of collaborations. Obviously, there have been other partners during the 3 years, including UTitle and the guys, Johan from the Beijing Institute of Technology, but also a number of participants that have spent hours watching balls moving around, which is not exactly the most funny experiment that you can make sometime, but it's harmless. That's already one point. Last thing, obviously, as we do in our competition, we have to thank the sponsors, in that case, INRIA and Central Nantes, and I think it was money well spent, given the results. And at last, I'd like to thank all the members of the committee for their somehow mixed reality presence. Some of us are present, some other in virtual reality. Thank you for attending this defense, for examining Etienne's work, and special thanks to Victoria and Sarah for getting up that early to listen to that story. As Ferran said, we would have been very, very happy to have you all in Nantes, but the sanitary situation has decided against it. And well, I just hope that will be meeting all together, whatever the carbon, whatever the CO2 it makes, to make it in a very near future. So thank you, everybody, and congratulations, Etienne.
Thank you. And so last but not least, Jean-Marie Normand.
I don't know, hopefully not the least, but thank you very much, Ms. President. So first of all, yes, I'd like to thank everybody, all the members of the committee, and especially Sarah and Vicky for getting up early, as Guillaume said. Thanks also to Jean-Louis and Valérie for being with us today and in this committee. Like everybody, I'd like to thank our co-supervisors, so Guillaume, Ferran, and Anatole. It was a very great pleasure to work with you and co-supervise our first PhD student together. And then regarding Etienne, so I just want to say that I was very lucky. I felt very lucky to share the same office with you and work with you during these 3 years. So some people might say that you're a bit grumpy. I don't know. Maybe some people might say I'm grumpy too. So maybe that's why we got along so well. But it was a real pleasure to work with you. As the guy said, you had very impressive qualities, like being able to do all these experiments mainly on your own, building boards and stuff, putting lasers together to have these RPDs and stuff. It was really impressive. And so I just want to say thank you for everything, and have fun in your new experiences in Brest. And I hope we continue working together even after you're gone. So thank you.
So thank you very much, everybody. So now it's time for the committee to talk together about the issue.
So, well, we'll have to ask you to make a short break, Etienne. That's the advantage for you. And Florian, if you can
We are back in.
Just coming. It's a bit cold outside, so it's just putting his hoodie off, and then he's ready.
Alors, Monsieur Étienne Peillard, donc le jury a eu le plaisir de vous écouter, a pu apprécier la clarté de votre exposé, la précision de vos réponses et la pertinence des réponses à leurs questions. Et en ayant également lu votre manuscrit, a considéré que vous étiez digne du titre de docteur en sciences pour l'ingénieur de l'École centrale de Nantes et vous en félicite car il appréciait grandement l'ensemble de ce qu'il a pu voir, de ce que vous aviez à montrer. Félicitations.
Merci. C'est à moi. J'ai pris un papier pour pas bafouiller. Du coup, je vais bafouiller, mais avec un papier. Alors, first of all, I would like to thank my jury for taking the time to read my work and attend to this defense. It has been a pleasure and an honor to be able to present my work and defend my thesis in front of you today. More generally, I would like to thank all those who participated in the elaboration of this work, my supervisors, my colleagues, but also the researchers with whom I was able to collaborate, as well as all the participants who took part in my studies. Like I like to say, that research is a team effort. And today, I want to state that I'm proud to be part of this team. En particulier, je vais continuer en français. En particulier, je voudrais remercier donc mes encadrants, Jean-Marie, Guillaume, Anatole, Ferran. C'est d'abord grâce à vous si cette thèse existe. Ce que j'y ai écrit, je l'ai appris de vous. Ce sont vos mots autant que les miens qui ont construit ce travail. Merci pour tout ce que vous m'avez apporté, votre temps, votre enthousiasme et votre bienveillance. 4 personnes pour un doctorant, ça peut paraître beaucoup, mais je peux vous assurer que chacun d'entre vous m'avait apporté des appuis à la fois complémentaires mais indispensables durant ces 3 années. Évidemment, je voudrais aussi remercier tous les gens que j'ai pu côtoyer durant tout ce temps, 2 équipes comme autant de familles où partager travail et plaisir, stress et réussite. Merci à vous, mes collègues et amis rennais comme nantais. Merci pour tout ce que vous m'avez apporté. Merci à toi en particulier, Flo, pour toute l'aide que tu nous apportes au quotidien et encore maintenant. Et merci également et en particulier à mes compagnons de bureau, Rebecca, Diane, mais aussi Martin. Me côtoyer aussi régulièrement n'est probablement pas des plus faciles, mais c'est avec beaucoup de plaisir que j'ai passé ce temps avec vous. Merci également à mes amis qui m'ont supporté, en particulier durant ces dernières années. 2020 n'a été une année simple pour personne et je tiens à vous remercier de vos mots et de votre présence ces derniers mois. Il me reste à remercier ma famille et en particulier mes parents qui, de l'autre bout du monde, continuent à m'apporter tout leur soutien et qui, je crois, se sont levés au milieu de la nuit pour m'écouter aujourd'hui. Encore une fois, merci à tous.
Félicitations, docteur.
Bravo, docteur. Chine.
Merci, effectivement.
Well, that's supposed to be the best moment for French PhD defenses, is about what's happening after the defense. But in this case, it's not the easiest part. I guess it's done now. We'll be exchanging emails. And again, I really want to thank you for attending this defense. And we're very proud about having you in the committee. We're, of course, very proud of Etienne's work. and of Etienne by itself. Anyway, so thank you very much. So I'm not going to say good evening for American colleagues, but at least have a good day now that the sun has awakened. And, I wish to meet you wherever, whenever, I don't know. Thank you again.
There are rumors saying that you have champagne in the room in Nantes, or even cider.
That's rumors.
Okay, cheers, and really congratulations, Etienne. It was really great.
Yeah, congratulations, Etienne. I am really looking forward to meet you in person.
Yeah.
Yeah. Bravo.
Bravo Etienne et bonne continuation.
Merci.
Bonne chance.
Merci.
Allez, bonne soirée à tout le monde.
Bonne soirée.
Salut Jean-Louis. Au revoir.
Bye bye.
Merci à tous.
Et
Thank you
merci.
so much. Thanks.
Yeah, thank you everyone.
Bye. Thanks a lot. And this is the end.
Attendez, j'ai un petit cadeau à donner. J'ai des cadeaux débiles à donner à Étienne. Alors,
Allez, maintenant, on va rentrer dans la partie.
On va juste attendre que ce soit coupé sur YouTube quand même.
Ouais.
Ah ouais, il faut couper.
Donc, Florent, il faut couper. Florian, il faut couper.
Flo, stop.